This is problem 2.89, and it's a problem that was worked out during recitation, but I wanted to make a video of it just in case you needed further clarification. So the acceleration is not constant with respect to time. It's wiggling back and forth in a sinusoidal kind of way. And we're being asked to figure out what the velocity is as a function of time and the position as a function of time. They want the velocity if at time equals 0, it's at rest, and they want the position if at time equals 0, it's its maximum departure. You got to realize that this thing is wiggling back and forth, so the maximum departure is basically that right there. That's x max. If you're plotting, for example, the x direction right here as a function of time. And I should erase all this before I turn in the homework, but I want to do a quick scribble here to show you this is the maximum departure. If you make this velocity with respect to time, then you get your Vmax. That's what that would be. If it's acceleration with respect to time, it's Amax. So parts C and D are asking for the maximum velocity and the maximum departure from the undisturbed state. You can easily see that if you look at the amplitude of this waveform, the maximum acceleration is A0 because the maximum value that the cosine can be is 1, and the minimum that it can be is -1. So that would give us this amplitude essentially being our maximum and I guess you can say minimum acceleration. So the maximum acceleration is just A0. If we're trying to figure out what the velocity is with respect to time, we're going to have to take the integral. Remember that the acceleration is the derivative of v with respect to time. So you can pull dv over here if you want to think about it that way. An infinitesimal dv is equal to the acceleration times an infinitesimal time, just like this. And what we need to do is add up the infinitesimals. So instead of a sigma sum, we use an integral. And the integral requires limits of integration. So we start off at an initial value of velocity of 0, because it says it's at rest initially. And we go to some future velocity v. So these are our limits of integration. It starts at rest and it has a velocity v after some length of time. The limits of integration over here have to be for time. So at time equals 0, the velocity is 0, and at some time t in the future, the velocity is t. So that's how we set it up, and now we simply plug in what our acceleration is from way up there. And so we go from 0 to v, 0 to t, and then this is the velocity. Oh wait, no, that's the acceleration. And we can't just pull it outside of the integral because it has some time dependence. So we have minus a0 cosine omega t times dt. And we can pull the integral, or the constant rather, negative a0 out in front of this. And if we look up in the integral tables in the back of the textbook, we find out that the integral of the integral of cosine omega t is the sine omega t over omega. So we have this out here, and then this right here is the result of that integral. We have to evaluate it at its limits of integration, 0 to t. And if you look up the integral of dv, it's simply just finding the final minus the initial. So there's our limits of integration, 0 to v. And so you say it's v, you evaluate this thing right here. At v, you evaluate it at v equals 0, so you get v minus 0. Do the same thing for this side. You evaluate all of this stuff at time and get this. You evaluate all of this stuff at time equals 0, and it turns this whole thing equals 0, because the sine of 0 is 0. That means that the velocity with respect to time is minus a0 over omega times sine of omega t. So it's also time dependent. It's wiggling back and forth with respect to time. Now that we know position with respect to time, we can take the integral of v dt to figure out what the position is. In the problem it says that at time equals 0, assume we start from our maximum departure from the undisturbed state. So that's why I changed it so that it says from initial to future over my integral with respect to time. I have to start off with my maximum departure, and I go to some unknown position x with respect to time. I plug in my v from up here in part A, and it's minus a0 over omega times sine omega t. I can look up that integral in the back of the textbook as well. So the integral of this one just becomes x evaluated at my limits. the integral of this guy right here is I'd pull off the a naught omega, and then the integral of sine omega t is cosine omega t over omega, so I put an omega squared right there. Evaluating it at its limits, I get x minus x naught. I put in this right here, so there's my first limit. And I subtract off, putting time equals 0 right there. The cosine of 0 is 1, so I get minus a naught omega squared. Now it takes some staring at this to kind of realize that this right here is the wiggle, and this right here is the maximum departure from the undisturbed state. That's the amplitude. So this thing that's out here is basically x max, and that's what this is right here. So it turns out these two things cancel out. This is the maximum departure from the undisturbed state. So these two terms cancel out. We got minus x max and the same thing that's over here. So shooting right to the end, part B, with those two terms canceling out, our position with respect to time is our amplitude times cosine omega t. Looking back at the results of part A, we can see that our coefficient in front of the sine, our amplitude, is the maximum acceleration, and the coefficient in front of this cosine is our maximum position, our maximum departure from the undisturbed state.